Hello and welcome to the discussion sessions of production technology, theory and practice. Now, in our last session we have finished discussing the machining processes, all right, and we have seen all machining processes, how they are performed, what is the mechanics of the machining processes, including the grinding, milling and so on. Now, we will start discussing the non-traditional processes. Now, let me give you a preamble that what is what we mean by the non-traditional machining. Non-traditional, as the name says, that this is not a traditional machining. Now, the traditional machining we have discussed in the machining processes. In machining processes, what we have seen is that there is a workpiece and a tool, they are interacting with each other, having a mechanical contact between them, okay, and a mechanical force is imparted to the workpiece to create high strain rate of deformation, okay, causing plastic deformation to occur in the machining zone, and as a result the excess material from the workpiece is segregated, is separated, all right. So, that we called as a conventional or traditional machining. Now, what was the problem in that? Okay, why we have to think of some kind of a non-traditional machining, all right. Now, in the while discussing the machining, we have said probably only one disadvantage, that is a lot of material wastage, okay. But along with that, what has to be considered also is that the metallurgist people, they are actually coming up with newer and newer materials, okay, metallurgy people, material science people, all right, specialists I mean. Now, those materials they are to be used in the industries like automobile industries, space industries, okay, machine tool industries, making the parts for different machines and so on. For machining those materials, and those materials obviously will have a different kind of characteristics, in the sense that their properties are better than the existing materials in terms of hardness, in terms of toughness and so on. Now, to making or fabricating those parts, those materials, the tool that we need to have in the traditional machining, the hardness of that tool had to be, tool material had to be very, very high, okay, higher than the workpiece material that we are going to produce. That becomes very big problem, because in that case the tool becomes very expensive, and many cases those tools are not simply available, okay, tool materials are not available. So, other problems which we had in the which we face in the traditional machining is that when the shape is very intricate, okay, very complicated, okay, or for example, we have to drill very, very thin, very small holes in a very thin job, all right, very fragile job, okay, or the shaft that we have to machine is let us say the tool of a micro EDM, okay, or micro machining. In those tools are very, very small in diameter, okay, they are very fragile, all right, and they are very slender. So, in that case the those kind of slender jobs they are not possible to have not possible to machine conventionally by imparting mechanical force, okay. First of all, you understand, and I also discussed it while discussing machining, that they cannot be held between centers. For example, if you want to have the turning, all right. Now, the other processes which can be used for that, of course, will be casting, will be metal forming, all right. But again, in those cases the surface roughness is not adequate. Okay. So, there are problems, overall there are problems in the conventional machining, apart from that we have to waste a lot of material. So, that forced us to think of some non-traditional machining. Of course, it is not a new machining. Authors claim in the books that this is the newer processes. I mean, it used to be newer processes, but now no more it is new, because it has been invented long time ago. So, what are those processes? Those new processes or the non-traditional processes, where probably we can machine any material of any hardness, okay, irrespective of the hardness of the material, irrespective of the intricacy of the shape, okay, and without wasting much of material. So, that means we have to eliminate all the drawbacks that we had in the traditional machining, so that these processes could be benefit us. Okay. So, those are the non-traditional machining which will replace or which will be implemented in practice when the traditional processes do not work, let us say. Meaning, suppose there is a very hard material, workpiece material, and we do not get the sufficiently hard tool material. Okay. In that case, of course, we go for the switch over to the non-traditional machining. Okay. So, now let us see, if you look at this slides. Okay. So, this will be the introduction to non-traditional machining. We are calling as a non-traditional. It is also called the unconventional machining. Okay. Now, the engineering materials overall, and that also we have discussed during the discussion on the engineering materials. So, they are subdivided into metals and alloys, okay, plastics and composites, and ceramics. Okay. Now, metals and alloys we are familiar with. What concerns the plastics and composites, ceramics, these are the materials which are getting more popularity, okay, and more popularity because of many reasons, because of the adequate properties of those materials in with respect to the metal or in comparison to the metal. Metals many times becomes very heavy. Okay. That is the probably one of the drawbacks of the metallic parts, that they are strong, they are rigid, their hardness is fine, but they may be very heavy. So, particularly in case of let us say aircraft industries, okay, there if you can save a bit of weight, and then it will be beneficial. So, therefore, the plastic and composites and the ceramics, they are getting more popularity, and because they have the definite advantages over the metals and alloys particularly. But then problem comes, then how to machine them. For example, as you know that plastics, of course, they cannot be machined like we do it for the metals and the alloys. They are the soft materials and they have to be handled in a different way. Composites, for example, they have the layers of materials. So, for example, we have the glass composites, okay, or fiber composites. So, in that case, when we try to drill, let us give an example of that, drilling. When you try to drill in a conventional way, in that case those fibers they break, all right, and they actually fracture inside. They cannot be plastically deformed. In that case, what happens is that the whole accuracy will not be good, whole surface roughness will not, surface finish will not be good, and so on. Ceramics, they are very hard materials and very brittle materials. So, machining these materials, they become very difficult. So, then the solution, as a solution, what has been thought of is the advanced machining processes. Okay. The machining processes with some advanced technology or advanced concept of the machining, concept of the removal of the extra material. By the way, when you talk about the advanced machining processes, here also we are actually removing the excess material, okay, like in case of the conventional machining. It is also a metal removal process, but in this there will not be any direct contact between the tool and the workpiece. This is the basic characteristics of the advanced machining processes. That is one, and the second basic characteristics is that there could be different kind of energies that we can use apart from the mechanical energy. Okay. So, let us see it here. Now, present day demand trends in industries like, for example, aerospace, missiles, automobiles, nuclear reactors, etc., that engineering materials having much superior properties. Okay. For example, ultra high strength, hardness, very high temperature resistance, difficult to machine by conventional machining methods, as I said. Such materials having these kind of properties is very difficult indeed. Now, workpiece material hardness is, in this case, what is happening is becoming much more than the existing tool materials. Okay. We have the certain limitation in the tool material so far, all right. Now, when we have the materials having much superior properties, then what has become is that the workpiece material hardness, workpiece of particularly these materials with these properties, they are becoming much more than the tool material hardness. So, how to solve the problem? Okay. Problem again can be solved by implementing the advanced machining processes, and as I said that there we do not have any direct contact between the tool and the workpiece like in case of the conventional machining, and we use different other energies than the mechanical energy. Of course, mechanical energy is also used, but apart from that mechanical energy, other energies can be used which will be much superior, and in that case the workpiece hardness will not be matter, in that sense that workpiece hardness does not matter in the advanced machining processes. Whatever is the hardness of the workpiece, irrespective of that, the machining can be done because of the technology, because of that particular technique that we will be using in the advanced machining processes. Let us see what kind of those. Now, why do we need advanced machining processes? Okay. Now, we have seen that limitation in the conventional machining methods, that is the workpiece hardness, surface roughness, 3-dimensional parts are very difficult to machine, complex geometries, okay, intricacies. Now, the increased workpiece hardness, that will decrease the economic cutting speed, that we have seen in the machining, that as the hardness is increasing, the cutting speed that has to be decreased, all right. That will be lowering the productivity, of course. Now, the rapid improvements in the properties of material, that means the workpiece hardness, strength, etc., increasing, as I said, that superior properties, okay, of the material that will be provided by the material science people or metallurgist people, all right. So, metals and non-metals like stainless steel, high strength, temperature resistant, super alloys, okay, like stellite, etc. This, then the tool material hardness has to be more than the workpiece hardness. This also we have discussed, the tool material hardness is 35 to 58% more than the workpiece material hardness. Then only the interaction can we can have the interaction between the tool and the workpiece to remove the excess material from the workpiece surface. Now, that requires much superior quality of tool materials, because we have to have the tool material hardness much more than the workpiece hardness, okay, and that, as I said, that 35 to 58% more. Why do we need advanced machining processes? Again, continuation of that. Product requirements also, apart from what we have said as the hardness, okay, superior properties, complex shapes. I told you earlier that if we have very intricate shapes, I will give you some examples also of such kind of shapes which are very difficult to produce with the help of the fabricate with the help of the conventional machining. Okay. Now, machining in accessible areas. While discussing machining, I gave you examples like automobile, the internal combustion engine cylinders, for example. There internally, when the two holes are meeting, there could be bars. If the bars are there, that means those small chips, they have to be removed. Okay. So, removing those bars by conventional sometimes very difficult, okay, and in many cases it becomes impossible using the conventional machining. Low tolerances, okay. Let us say 10 micrometer tolerance. So, maintaining 10 micrometer tolerance is very difficult, because in that case machine tool has to be very stable. There should not be any kind of vibration or any kind of relative movement between the tool and the workpiece, rather than which is desired, okay, what is given. In case there is any small vibration, so you understand that it amplitude is more than or even around 10 micron, in that case this kind of a tolerance, say 10 micron, cannot be achieved. Okay. Next is the better surface integrity. Okay. Better surface integrity, that is no surface defect. That means there should not be any scratch, there should not be any fracture or anything, there should not be any surface defect. All right. That actually is difficult by the conventional machining, because many times what happens is the chip entangles with the workpiece surface. Okay. The tool wears out and the flank face starts rubbing the already machined surface, spoiling the surface. All right. Or tool wear, overall tool health is deteriorating as the cutting process goes on. So, therefore, as the cutting process goes on, the surface integrity may not have the desired one, okay, and surface defects may occur. High surface finish in the nano level, for example, that is the RA values are in the nanometer. RA is the I will show it to you while discussing the surface roughness in the metrology section. All right. So, there the high surface finish we have to obtain in many cases in the nano level, that is the RA value, those are the asperities, undulations, this is the property of the undulation, this value should be in the nanometer. Okay. It is very, very small. Miniaturization of the products. For example, we have the landline phone and mobile, okay, old computers and laptops. So, just imagine from the landline phone we switched over to the mobile, and the parts that we have in the landline mobile, those parts are easier to make rather than the parts that we are having right now. So, we have miniaturized, all right. And if we compare the old computers with the laptops, okay, laptops is much compact. So, it has been miniaturized in comparison to old big computers that we used to have earlier. We need also high material removal rate, because we need to have the high production rate. So, along with all those requirements, all right, all those requirements are not possible all the time for to satisfy in the with the conventional machining, with the normal machining that we have discussed. So, therefore, we have to actually go for the advanced machining processes. This is the justification why the advanced machining processes came into picture. Okay. High production rate while machining difficult to machine material. Difficult to machine material, anyway it gives the difficulty as the name says for machining, because its hardness is very high, tool wears out very fast, you need to have the high force, high strain rate of deformation to be imparted, and so on. So, then along with that, for those materials we need to also have the high production rate. Okay. Low cost of production, cost should not be very high. Precision and ultra precision machining, that is in the nanometer machining. So, these are all the increasing demand in the industry, because we are progressing, we have to go faster now, we have to have the miniaturization, we have to have the more precision machines. Okay. So, that require of course requires material removal in the form of atoms and molecules. Okay. So, we are no more now limited to the, we cannot limit ourselves in removing the chips, although we say small chips, these are not in nanometer, these are in millimeter. Okay. These are big chips, I mean, in comparison to when we talk about molecules and atoms. Okay. So, this is the solution, which is the advanced machining processes that we have to come up with to solve these problems that we face in the conventional machining. Okay. Now, some examples, let us see. Fabrication, when we do that, and when we talk about that, building of machines, structures or process equipment by cutting, shaping and assembling components made by the raw material, okay, made from raw material. So, this is the fabrication. Okay. Now, this fabrication may have the meso or macro fabrication or micro fabrication. All right. Now, meso and macro fabrication, here the process of fabrication of structures that are measurable and observable, the dimensions are bigger, okay, is visible by naked eye. We can see them because they are bigger in dimensions, and the dimensions are normally more than or equal to 1 millimeter. So, you can understand that this is quite big for them to see by naked eyes. All right. But in case of micro fabrication, when we talk about that, the process of fabrication of the miniature structures we talk about, okay, or features of the micron sizes, and that fabrication process needs microscopic equipment for the measurement, because the dimension lies between 999 micrometer to 999 nanometer. Okay. So, within that the dimensions are lines, and as you can see that this is less than of course 1 millimeter, and they are, some of them are not even visible with naked eyes. You have to have the microscope to see them, okay, because in that case, as we said, the material is removed in the atoms, size of an atom or molecule. Okay. Now, non-traditional machining processes overall, all the processes, they can be classified based on the kind of energy used. As I told you that here in contrast to the normal machining processes or conventional machining processes, we not only use the mechanical energy, but we can use different kind of energy, because as you understand that we have to now machine material of any hardness, which was not possible with the help of the conventional machining. So, therefore, the kind of energy that used is the mechanical energy, thermoelectric energy and the electrochemical and the chemical energy. These three basic groups of energy that is used in the case of the machining processes, non-traditional. Now, in the mechanical, this is abrasive jet machining, this is normal machining processes. Okay. Abrasive jet machining, normal machining processes, we mean to say that still it is non-traditional, but this is not the finishing process, okay. It is a machining process. So, the abrasive jet machining, there is one which uses the mechanical energy, details of that we will talk about a little later. Ultrasonic machining, where as you can see by name, the ultrasonic frequency of vibration is used. Here abrasive jet, by name it says that the machining or the material removal is accomplished with the help of the abrasive jet, which impinges the workpiece surface. All right. Water jet machining, again the removal of the material from the surface by a water jet, again that will impinge the workpiece surface with very high force, and I will show you the pictures, I will show you the details. Okay. Abrasive water jet machining, Okay. So, abrasive water jet machining, that means you are mixing abrasive here. So, it is abrasive water jet machining. All right. Here the water stream that we were using, water jet that we were using in the water jet machining, there the abrasive powders are mixed. Okay. So, there it becomes the abrasive water jet machining. In the finishing, we have the abrasive flow machining or abrasive flow finishing. So, here also you can see that the abrasive powders are used, okay. But in comparison to this abrasive water jet machining, if this is the so to say rough machining, this can be used for the finishing. Okay. Magnetic abrasive finishing or magnetorheological finishing. So, these are the processes which have been in practice recently, okay, not very long ago it has been started being used. All right. Now, the thermoelectric energy, using the thermoelectric energy, the processes which are in practice are the plasma arc machining. Okay. So, there a plasma arc is used to remove the extra material from the workpiece surface, laser beam machining using the laser beam, using the electron beam machining. Okay. Electron beam is used for removing the material. So, these are all the beam technology, that means using different kind of beams like plasma arc, laser beam, electron beam, we can actually remove the excess material. Electric discharge machining, EDM, this is one of the very popular processes, okay, which is actually the thermal process, all right, and it is actually the thermoelectric because electricity is passed, of course, voltage is passed through. Ion beam machining, another beam technology. So, here you can see that all these here most of them are the beam technologies, that means we create the thermal energy, we create the temperature, high temperature, okay, and that actually can melt, evaporate the workpiece material, whatever is the hardness of the material. So, there that means we are saying that we are using thermoelectric energy, okay, or electrochemical and the chemical dissolution. So, this is the electrochemical machining, this also very popular like the EDM, all right, this is called the ECM, electrochemical machining. Chemical machining, etching for example, okay, kind of chemical machining. Biochemical machining, biochemical machining also came into picture recently, it was not so popular earlier, but because we have different materials plus soft materials and nanoscale when we have to machine, then those biochemical machining are very popular nowadays. Okay. These are some of the complex shaped workpieces, okay, and you can see that these workpieces are really very intricate. For example, turbine blade, okay. This is the cross section of a turbine blade and this is the turbine blade view, and you know that in the turbine blade, first of all that shape is very intricate, okay. Machining of this kind of a shape is itself is a challenging job. Second thing is that it actually works with the burnt gas which is very high, which is of high temperature. So, overall the turbine works in the environment of very high temperature and pressure, all right. So, these blades are to be cooled down, all right, and therefore, there is cooling air passed through the holes and those holes are very intricate holes. These holes are like this. This is the theoretical profile that has been designed and this is actually the machine profile. The hole is like this, okay. This is the experimental profile. Hole is not a straight hole, but it is a kind of like this. So, these are the kind, this is kind of a machining that we have to do and that too in a material which is very hard. For example, it is an Inconel material, okay. So, here is the example when such kind of a hole is drilled, this is the actual profile, okay, using the electrochemical machining, okay. Or for example, if you see the this is the this is a part where you can see that male part and this is the female part and you can see the intricacies, okay. This is also kind of a turbine blade, all right. Here also there is very small holes, you can see that, and through these holes the cooling is done, okay. And making these holes conventionally is almost difficult, almost impossible. So, therefore, precision wire electro discharge machining is used for making such kind of parts, so that the precision is maintained as well as such kind of intricacies can be obtained. So, this is highly exaggerated view of the taper 3D cutting using the travelling wire electro discharge machining. So, you can see that the intricacies of the surfaces, okay, and they have to be their precision has to be very high, okay. And overall the material is very hard, it is very difficult to machine, okay. So, therefore, all these criteria have to be satisfied, and the traditional machining many times they are not successful in creating these jobs, all right. So, non-traditional processes have to be used for that. So, you can see that with the help of the wire EDM or with the help of the electrochemical machining or with the help of the wire EDM, normal wire EDM also, like this kind of intricate holes, this kind of intricate shapes can be machined. Or this is the part of a helicopter turbine. Now, the holes here are also very complicated because the surface is not the straight cylindrical surface. So, these are drilled by the electron beam machining, EBM. Okay. Here this is exaggerated, actually amplified under the microscope. This is each hole here, the diameter is 0.09 millimeter, okay. And here in 1 centimeter square there are 4000 holes, okay. So, hole density is 4000 per centimeter square. So, in a centimeter square area there are 4000 holes, okay, and workpiece is stainless steel, thickness is 0.2 millimeter, okay. So, just imagine that how how would it be possible to drill such holes in such a thin workpiece 0.2 millimeter in such a hard material like stainless steel and with such density of 4000 holes per centimeter square. That means, the distance between the two holes is very, very small, right. So, this can be done by the electron beam machining, and this has been done by electron beam machining, and the time taken is 10 millisecond per hole, okay, per hole 10 millisecond. This is even difficult job because it is a 0.06 millimeter hole diameter, okay, 6 micron. That means, the hole density is 200,000 holes per centimeter square, here it was 4000. So, and the thickness is 0.12 millimeter, even thinner, and the time taken is 2 microsecond per hole. So, these are the facts for the also done by the electron beam machining, okay. Facts of the non-traditional machines, which are of course cannot be done with the conventional machine, okay. Here you can see that abrasive media acts as a self deformable stone, okay. Now, some important characteristics of the abrasive machining processes and machine tools. Performance is independent of the strength barrier that I said, okay. Now, the performance depends on thermal, electrical, magnetic and chemical properties of the workpiece material. So, this is straightforward, you understand that depending on the workpiece material properties, okay, we will have the choice of a particular process and the performance. Use different kinds of energy in direct form, okay. Directly we are using some sort of energy, all these energies that I have already told you earlier. In general, low material removal rate, but the quality is better, quality of the product is better, okay, when we are comparing with the conventional machining, all right. Now, comparatively high initial investment cost of machine tools and high operating cost. This is the disadvantage, because the cost will be more, and of course, the production rate will be less because the material removal rate is very less, and of course, the time taken for making, for example, in case of the electro discharge machining or electrochemical machining, time taken is very high in comparison to machining, conventional machining, but here the quality is better, the accuracy of the machining, the overall quality, surface roughness can be better. Non-traditional machining therefore, by definition is mostly based on removal of materials using tools that are harder than the materials themselves, of course. New and novel materials, because of their greatly improved chemical, mechanical and thermal properties, are sometimes impossible to machine using the traditional machining processes. I am simply summing up whatever I have said earlier. Now, the traditional machining methods are often ineffective. Traditional is the normal machining processes that we have discussed. In machining, hard materials like ceramics and composites, I already told you, or machining under very tight tolerances as in micro machined components, for example. Okay. Therefore, the need to avoid surface damage, okay, that often accompanies the stresses created by conventional machining. All right. So, we have the surface damage. I told you that in the conventional machining very often because of the entangling, particularly of these chips, or the high friction between the workpiece and the tool and so on. So, those can be avoided in case of unconventional machining. Example is the aerospace and electronic industries. They are classified under the domain of non-traditional processes. Okay. So, this is the summary of whatever I have said, and these are the justification for selecting the non-traditional processes. Okay. All right. Now, the classification once again I will define here in terms of in wordings, that this can be classified according to the source of energy used to generate such a machining action. Mechanical, it can be thermal energy, chemical and electrochemical. I have shown it to you in a table. Mechanical is erosion of the work material by a high velocity stream of abrasives or fluids, okay, or both. This is an example of the mechanical energy. When we have the impinging of the abrasive materials, that means the grains, okay, aluminum oxide, silicon carbide grains, okay, diamond grains, those who are very hard particles, they can impinge the surface with a mechanical force and have an impact and then remove the material. Okay. It can be thermal energy. The thermal energy is applied to a very small portion of the work surface, causing that portion to be removed by fusion and or vaporization of the material. The thermal energy is generated by conversion of electrical energy. Okay. So, those we have given examples like electron beam energy, electron beam machining, like laser beam machining. So, we pass electricity to in a circuit and we convert this electrical energy to electron beam, for example, to create the plasma arc, for example, okay, and so on. So, those beams are then used to create very high temperature in a very small area, okay, very small area. I will show it to you, and then that can actually melt and evaporate the material from the workpiece surface. Okay. Electrochemical dissolution, as I said, that mechanism is the reverse of electroplating. Okay. We know about electroplating. This is very famous process which you must have studied in class 10-11. So, electroplating, opposite to electroplating, here it is depositing, here it is not. So, it is removal, therefore, it is the opposite, it is the reverse, that is the electrochemical, and we call it electrochemical dissolution. When it is dissolved, material is dissolved, okay, in the solution. And chemical energy, that is most materials, metals particularly, they are susceptible to the chemical attack by certain acids or other agents. Okay. In chemical machining, chemicals selectively remove material from portions of the work part, while other portions of the surface are protected by a mask. Okay. So, this is what is done is that the surface is masked first, and that mask is such that it will not be affected by the acid, all right, or by a certain chemical which is being used. Now, those portions which you need to be attacked, need to be removed or machined, in those are not masked. So, then if it goes through the chemical, or if you pour chemical on top of it, okay, then those portions which are exposed, that will be only etched or marked, and other portions are not, because there is a mask. Okay. That is the process of the chemical machining, and this is quite well known. This is very popular in even the household appliances. Okay. So, therefore, in one word, non-traditional machining processes can be classified into 3 categories, where we are having different kind of energies used: mechanical, thermal, chemical, and electrochemical. In mechanical, we have the ultrasonic machining, water jet machining, abrasive water jet machining, and the ion jet. Okay. Thermal, we have the electrode discharge, electron beam, laser beam, okay, ion beam, plasma arc, and so on. Chemical, we have the chemical machining and electrochemical machining basically. Okay. So, mechanical machining, that is, let us say ultrasonic machining and water jet machining, these are the examples of the mechanical machining. All right. By mechanical machining, we mean to say that non-traditional machining using the mechanical energy. Okay. They are typical examples of single action mechanical non-traditional machining processes. Okay. Ultrasonic machining and the water jet machining. The machining medium is solid grains suspended in an abrasive slurry in the former, while a fluid is employed in the water jet machining. So, in the here in the ultrasonic machining, the solid grains are used suspended in an abrasive slurry. So, abrasive slurry means that abrasive mixed with some kind of a fluid. Okay. So, the entire thing is a fluidic material where we have the abrasive materials, and that is flown between the tool and the workpiece, the gap between the tool and the workpiece, because as I said earlier that there is no direct contact between the tool and the workpiece like in the case of the normal machining processes or traditional machining processes. Okay. The machining media is solid grain suspended in an abrasive slurry in the format therefore. Okay. And here in case of water jet machining, a fluid is employed. Now, the introduction of abrasives to the fluid jet enhances the machining efficiency. Now, as I said that earlier we had the water jet machining, and there we are introducing, we are mixing with the abrasive powders. Okay. That abrasive powder actually enhances the material removal rate. Okay. So, therefore, it is added and is known as the abrasive water jet machining. Similar case happens when ice particles are introduced as an ice jet machining. So, ice jet machining is also used rarely, but these are used when the ice is included in place of the abrasive material, okay, abrasive grains. So, you can see in this figure also the mechanical non-traditional machining, okay, processes. They are basically subdivided into ultrasonic machining and water jet machining. Ultrasonic machining is the abrasion, okay, and here we have the, well, abrasion is the mechanism, okay, of material removal, it is a mechanical abrasion, and abrasives are used as particles, they are the slurry, and we have the workpiece here. All right. In this case, the water jet machining, this is the cutting process happens, and the medium used is such some jet, which is the water jet, and this is a fluid and the work interaction between the fluid and the workpiece. Okay. Now, in case of thermal machining, similar to the previous one table, thermal non-traditional machining processes removes material by melting or evaporation, vaporizing the workpiece material. Okay. Many secondary phenomena occur during the machining, such as micro cracking, formation of heat affected zones, okay, striations, etc. So, these are the phenomena which happens during the machining. So, because of that the material is removed basically. So, these are the mechanisms through which the process goes and the material is removed. Material is removed by, again, this is the thermal process. So, it can melt and evaporate, all right. So, in between we can have this phenomena like micro cracking, formation of the heat affected zones, striations and so on. The source of heat could be plasma as during the electro discharge machining, and photon beam machining in case of photons, in case of photon beam machining as during the laser beam machining, okay. Electrons in the electron beam machining, ions in the ion beam machining and so on. So, you can see that there are different kind of sources which we are using, okay, heat source that we are using, but all of them they are creating the very high temperature in a very small area. So, therefore, that high temperature actually melts and evaporates instantaneously irrespective of the hardness of the workpiece. So, that is what we are saying, that this is how the material is removed by melting and evaporation. Okay. Chemical and electrochemical machining, here the mechanism is the following. So, these are the electrochemical machining, these are the representative processes. Okay. Here if you can see that electrochemical dissolution is the mechanism, okay, and the ions are used as the source, electrolyte is here, electrolyte is used and the interaction with the workpiece. Okay. Chemical machining, all right, here the chemical dissolution is there, here also the ions are used to etch the workpiece. So, the interaction between these ions and the workpiece by the etching. So, chemical milling and photochemical machining comes in the chemical machining. Here it is the chemical milling and here it is a photochemical machining, or the photochemical blanking also it is called. All use a chemical dissolution action. This is the chemical dissolution. This is the see electrochemical dissolution and chemical dissolution. So, these are the mechanism of material removal, how the material is removed. Okay. In thermal case, in thermal we said that this is melting and evaporation. Okay. In case of electrochemical machining, it is electrochemical dissolution. In case of chemical milling or the photochemical machining, it is the chemical dissolution, okay, to remove the machining allowance through the ions in an etchant, through the ions in the etchant, and this is is from the workpiece, material from the workpiece is removed. Electrochemical machining uses the electrochemical dissolution, okay, to remove the machining allowance using the ion transfer in an electrolyte cell. So, in the electrolyte cell the ions are transferred by help of the electrochemical dissolution, the material from the workpiece is removed. Therefore, in these advanced machining processes, it is interesting to find out that can we use all kind of sources. For example, water. Can water cut the metals? Answer is yes, but how? Okay. Here is how, that is water jet machining, abrasive water jet machining, abrasive jet machining. So, we can see that if the water is forced at a very high speed, okay, through a very narrow nozzle with a less diameter, in that case the wood, soil, they actually can be cut. Okay. Now, if we use the sand and the water together, then of course harder material like stone for example or aluminum, they can actually be machined, or they can, the material can be removed from the harder surfaces than the wood and the soil, okay, because we have the abrasive water jet machining, and in this case the high force of water along with the impinging of the abrasive particles, hard particles into the surface, that actually helps in removing the material more. Okay. Or for example, the abrasive jet machining. it is only the air and the abrasives. Okay. So, that will be here for example, we have again stone and aluminum, here it is water and sand, here it is abrasive and sand and air. So, sand and air or water and sand, they actually can create the brittle fracture. Okay. So, when the the abrasive material impinges the workpiece surface, the workpiece surface can be fractured, and when it is a brittle material, this is easily fractured. Okay. So, it is convenient for removal of material from the brittle surfaces, particularly that water sand and abrasive water jet machining, abrasive jet machining and so on. So, particularly the abrasive jet machining, they are popularly used for removing the material from the brittle surfaces, because it is the material removal mechanism is the brittle fracture. It fractures the material and removes that way. How does it work? Okay. Water abrasive particles makes it to happen. Velocity of the abrasive water jet can be as high as 900 meter per second. 900 meter per second is very high speed. In fact, that jet, if it comes on the human being, it can actually damage the skin and the flesh. Okay. So, it is a very high speed, and if you remember, if you have seen that sometimes the riot police has a gun, water gun. Okay. So, there also the high speed water jet is used to disperse people, of course, to scare them, not to damage, but the purpose is to scare them. But nevertheless, if it falls on the human being, human being cannot sustain that force, and they can actually fall. So, they run away. This is to disturb people, so that they do not gather together. This is the water gun. Okay. Water jet cutting in details, also known as the hydrodynamic machining. Okay. Hydrodynamic machining means this is the machining process or removal of excess material by the hydrodynamic force. Uses a fine high pressure, high velocity of water directed at the water surface work surface to cause the cutting of the work, to cause the material removal. So, if you see the diagram here, this is the workpiece. Now, here is the nozzle and there is a valve to regulate the pressure of the water, and here we have the source of high pressure water coming from here. The valve regulates that pressure and it throws this water to the nozzle. From the nozzle, the water comes through a very tiny hole, okay, and the very fine water jet is directed towards the workpiece from a distance, and this distance between the nozzle and the workpiece, this is called the standoff distance. This distance is very important. Okay. So, in each of these unconventional machining processes or non-traditional machining processes, there the standoff distance should be maintained in a proper way, and the standoff distance means that there is a particular distance between the tool, okay, and the workpiece. They are not in direct contact. If the standoff distance it fluctuates, it may actually create the inaccuracy in the machining. For example, here what happens is that as the standoff distance increases, for example, then the value which has been calculated, in that case the strength of the water jet falling on the workpiece surface will be less. Okay. And another thing is that if the standoff distance is inappropriate, in that case the tapering may happen here. Okay. Here the diameter will be less or more, and here the diameter will be accordingly, I mean not according to this diameter, they are not the same, therefore there could be a tapering, okay, and that tapering is very often it is called the overcut. Okay. The overcut can be of this type. So, like this, for example, it can happen that the energy is maximum on the top, and as it goes inside the energy becomes less and the diameter becomes less. So, this may happen actually, I will come to that in details in other processes. Here the nozzle diameter here is the 0.1 to 0.4 millimeter. Okay. So, this you can see the very small diameter of the nozzle, and there is a pressure which is created by the high pressure water, source of high pressure water, and through the valve. This is up to 400 megapascal. So, this is also a very high pressure, all right. The velocity is 900 meter per second. So, because of this pressure and the nozzle diameter which is up to 0.4 millimeter, the velocity becomes 900 meter per second, and as you can see that this speed of the water jet is very high, and the fluid is pressurized by a hydraulic pump. There is a hydraulic pump here, that is the source. Okay. Important process parameters are that the standoff distance between the nozzle and the workpiece, okay, is about 3.2 millimeter. So, 3.2 millimeter is the ideal or is the optimum standoff distance. As I was telling you that standoff distance is very important, and that can be optimized depending on the pressure that you are creating, depending on the velocity that you are creating, and the workpiece surface and the workpiece material also. So, that has to be kept constant all the time, okay, so that the accuracy is maintained. So, here it is about 3.2 millimeter. Nozzle opening diameter affects the precision, of course. Okay. You understand, as I told already, water pressure high for thicker material. Of course, when the material is thick, that is the thickness of this workpiece material is more, then you need to have the high pressure, because the force required to impinge by the water jet throughout the width of the workpiece should be more. Okay. Cutting feed rate, the velocity at which the water jet nozzle is traversed along the cutting path. So, as you understand that this is not only for the cutting or putting of the material, but it can be used to make a contour. For example, let us say we have a material like this, okay, or we have a plate like this, and we have to have a contour shape cut from here, okay, like this. So, this can be cut through the nozzle, and that is then the nozzle has to be traversed. So, this is called the cutting feed rate. This is the feed rate at which the nozzle will be moved to make this contour, okay, to cut this profile. Okay. This I will show it to you in more details later on, that is why I have removed it. Now, here the material water jet machining machines are here. You can see that this is the nozzle actual in practice, and you can see that very high pressure water jet coming through the nozzle, and it is making a groove like this. So, this is the traverse that I was talking about, that the nozzle has to traverse like this along the path of the groove to make that. So, these are the slots or the grooves, okay, made here. It can also make a through hole like this. So, for that it has to impinge first, make the entire material cut in one place, and then it will traverse like this, and therefore, the entire material will be removed or the hole will be obtained in that case. Okay. So, the rest of the material in this section of the non-traditional machining I will discuss in our next session. Thank you for your attention.